Can you see my screen?
Recording is on.
Great. Finally. Okay. Um, yeah, I took a lot of time. Let's see. So today we are going to discuss these two, linked list insertion, linked list palindrome. Anyone heard of problems before? Basically, linked list insertion determine if two linked lists intersect. So if yes, return the intersecting one. Basically, if there are two linked lists are there, and at any point of time, if they intersect, we need to determine whether they nodes are intersecting, and if they are intersecting, what is an intersecting node? Did you hear this problem before? Anyone?
I have not.
Um, okay.
Questions on
No, but
palindrome I have tried, but not intersection I have. I haven't
okay,
tried it.
okay, okay. So, but you understand it. Let me explain a little bit with the diagram here, and then we can dive into the algorithm. So here is intersection. So let's say we have something like this. So these are the nodes. Okay, 3 goes to 1, 1 to 5, 5 goes to 9. Okay, and 5 goes to 9, right? Yeah. Now, um, yeah, this is another node 7, 7 to 2, 2 to 1, and okay. Let me see. Is it intersecting one or it's a different one? Intersecting. Yeah, this is 3159 and 721 and node 446. But 3 goes to here is n7 and 9 goes to n2. Okay, that's the thing. And 9 goes to n7. So 9 goes to 7 and 7 connected to 2 and 2 connected to 1. Okay, now there is one more node here. There is one more node 4 and 4 and 6. Let's see, 4 goes to 6 and again 6 connected to n6 here and 6 connected to n7. So like this. Okay, so there are two linked lists. The first list has 1 2 3 4 5 6 elements, and the second linked list has 1 2 3 4 5 elements. Okay, so now if you look at that, both intersecting at the node 7, correct?
Yes.
So there are two linked lists. So basically the next node of 9 pointed to the 7 and next node of 6 also pointed to the same node 7. So here this is intersecting in the sense by the address. That means not by the value. So here is the thing. So if you look at here, here is the n7, right? N7 node connected to n9, n9 connected to 9 connected to 7, and also here n6, the 6 connected to 7. It's exact same node we are connecting. So now we need to figure out, do we have intersection? Yes, we do have intersection, right? And what is the intersection node? 7.
7.
7 is, so how can we figure out? The given algorithm is the inputs is two linked lists with the head nodes. So we will have pointer to 3 and then a pointer to 4. We will have two pointers which will give you the head. So how can we determine whether these two linked lists are intersecting or not? So if they're intersecting, we need to say either true or false. And if this is true, what is the intersecting node? And it's 7. So any ideas how can we figure out?
What is the space and time complexity? We have to come up with a solution. Suresh.
Let's say you can take whatever. Like let's say there is no restriction. Think about how can we do without. So if you want to use any data structure if required, but what is the main how can we do this? Basically, if you start looking, if you start navigating with these nodes, right? So within 1, 2, 3, 4, 5 steps, you finish the list two, and it takes another 4, 5, 6, 7, right? 1, 2, 3, 4, 5, 6, 7. So 7 steps you finish this first list. So how can we determine when they are meeting, right? So let's say we have something like this: 3, 1, 5, 9, and 7, 2, 1, and another list which is like this: 4, 6, 7, 2, 1. So here the values are same, but it's a separate node. It's we are not reusing, we are not using the same nodes or same address in the memory, right? So these two, if you are looking at this kind of list, this is not intersecting, right? So this is a different list and this is a different list. Even though the numbers are same, 7, 2, 1 here, 7, 2, 1 here, but the address are different. So these are not intersecting, right?
Mm.
So the first this first the first input is intersecting, and what is the main difference between these two? So I can explain.
The
So
length,
the main difference. Go ahead. Go ahead. Length is
the
different.
length,
That's good point. Exactly. So there is no
yeah.
guarantee that both the lists are same length. But if there is a condition like that, let's say both the both the lists are same length, does it help to find uh, an intersecting node? You came to the really good point actually.
Both are in the same length in the sense, yeah.
It will be very
Yeah,
easy, right?
yeah.
How can we? Yeah.
We can traverse using the head pointer of the both list and
Uh-huh.
find out whether the next pointer we are pointing to, the both list is the same.
Exactly, exactly. That is the actual algorithm. That's it. So basically, if you look at this, let's say we don't have 3, 1, we have only this is the list. Let's say, let's consider this is the input, right? We have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Both the lists have same number of elements. Then it is simply just navigating. We will see. First, we will take two pointers like P1, P2. P1 points to here, P2 points to here. Is both are same? No. P1 points to here, P2 points to here. Is both are same? No. Let's go to the next node and next node. Is both are same? Yes. P1 and P2 point to the exact same address, right? Then it's intersecting, right? So if you traverse from here, if you traverse here, you can complete, like you can go all the way to the end without even matching. At any point of time, P1 never equal to P2. So if we are not checking the data, so it's always like n1 equal to n2 or not equal to, or p1 not equal to p2. That condition will give you the address comparison. Okay. So you arrive at the right solution there actually. But the problem here is inputs are like the lists are not same length. How can we you know figure out that? So Sicily, I understand, right? If the lengths are same, it's just a matter of comparing each node, whether you find the node same equal, or if you don't, if you go to the end of the list, there is no intersection. Correct.
Mm.
So now the problem here is lists are not same length.
We can subtract the length of the first list from the second list, and
Exactly.
the with the
Hmm.
remaining number we can start with the biggest list. In the biggest list we can start with that number.
Exactly. That's exactly the algorithm here. So what we need to do is let's figure out. We don't know. We will get two linked lists, right? Let's say head one and head one. and head 2. There are 2 pointers. Head 1 points to here, head 2 points to this linked list. At the beginning of the algorithm, we don't know which one is bigger. We don't know how many nodes in each linked list. So, as Karanya said, we need to figure out first we need to figure out the difference between the lengths. So what is the length of this node, this linked list? What is the length of this linked list? And we will figure out the difference. And then once you found the difference, we will proceed whatever the longest list in whichever is the longest list. We will proceed that many number of nodes, and then we will start this comparison. So now let's see what is the length of this list one. How many elements in the list first list?
7.
7.
7. How many elements in the second list?
5.
5.
5, right? So equal to 2. So this is the difference is 2, right? So what we need to do is we need to get this difference, which is number 2, and also we need to figure out which one is the bigger. So here we can simply say we can figure out basically, we need to figure out which one is bigger. So the first list is bigger, right? Now we need to traverse 2 nodes in the first list. That means we need to traverse this one and then stop there. After that, we need to traverse both at the same time until you find a either you find a in common node, or it will go to the end of the list, right? You guys understand the algorithm?
Yes.
Okay. So
Yes.
now there is one, yeah. So there is one more here. So before even that, so basically what are the steps here? First one is finding the lengths. Second one is find the difference, just minus, do the subtraction. And third step is proceed the longer list, or find the longer list. And next one is proceed the longer list until that many difference number of nodes which are equal to the difference of the lengths. Now last step is fifth step is basically going the same nodes at the same time, like comparing the nodes. And if you look at these many steps, we don't need to do these many steps for every input. Basically what I'm saying is, um, let's look at the second input. If you look at the second input, so we will get the same length here, 7 here, and then 5 here. And we no need to do all these 5 steps if we know that both lists are not intersecting. So what I'm saying is, by finishing the first step itself, we can figure out whether the lists are intersecting or not. So if you look at the inputs here, the main algorithm or the main input here is, if they are intersecting, ultimately they will end up having with same end node. They could be intersecting at 7, they could be intersecting at 2, or they could be intersecting at last node, which is 1. So what I'm saying is, if the last node is not common, right, they are not intersecting at all. Correct? See, if you look at the second input, right, last node, this one is different from this one. So because this one is somewhere in the address like 1111, let's say, and this is 2222, we don't know the exact address, but these 2 nodes are different in the memory. Correct? So we can see whether these 2 nodes are equal. If these 2 nodes are equal, then we need to do rest of the steps. If the 2 nodes are not equal, then we can simply say, by after step 1 itself, we can simply say the linked lists are not intersecting and there is no intersecting node, because there is no other way of intersecting, right? One last node, either they should intersect at the one at least, or they should intersect at any of the nodes before. But if you intersect it at any of the nodes before, like 7 or 2 or somewhere, they end up navigating to the exact same end node. Correct? Is that clear?
Yes.
So
Yes.
that is the first condition. So basically, while calculating the length itself, after getting the lengths, we will see whether the tile node, whether the last node are same or not. So we will do two things at the same time. In the first step, what we do is we will calculate the size of the each linked list, and also we will compare like what are the tile nodes. We will extract the tile nodes, and after step one, we will compare is the tile nodes are same or not. If they are not same, boom, we no need to do anything, just return say false, not intersecting, and just return null value because there is no intersecting. But if the tiles are same, if the tile nodes, the last nodes are same, then we will do the rest of the steps. Okay, so that's exactly what we do here. So I put a different methods here. There is a test run, test case one, test case two. There are two test cases I added, and here is pretty common, thing, printing the linked list, okay, and printing the result. So result is basically I'm saying like node, and if the node is null, linked list are not intersecting. If the n is not null, and here is the actual link, like the intersecting node. But what is the actual algorithm? So here is the actual algorithm. So let me expand here. Is it visible, the zoom and everything?
Yes.
Okay. So here what we are doing is, as I said, we will get link list one, list two. These are the two pointers which will point to the head of the linked list. So now just this is a very basic base condition. If in case any of the things are null, so there is no intersecting node, simply return null. So otherwise, this is the first step. Find the sizes and not trial. It's tile, TAIL, right? Tile nodes, like last node basically. So what is the last elements? So as I said, we are getting two kinds of information from each, right? So get tile and size. So here is the method we created. So what are we saying is, hey, this is the linked list, give me these two result. The result is basically it's a class we created. This contains two things. This contains the tile node, what is the last node, and also the size. So I created a small, why we created a class is we want to capture two sets of information, right? It's the best way to do this. So we cannot return two values, right? You cannot return both node and integer from a single method here. That's why this method returns a result kind of object. That result object has two things. For the list one, what is the size, and for the list one, what is the tile node. Okay, so let's dive into that. Or yeah, let's dive into that method. So how are we going to find? It's very simple. So if list is null, if in case anybody just call this method without having any proper address, if the list is null, there is no result. Otherwise, if the pointer comes here, that means list is not null, at least one element is there, right? So that's why we are initializing size with 1. Now we don't know how many elements, so we are calculating now just by taking a pointer current equal to list, current not next not equal to null, and size plus plus. So this can, as I said, the linked list conditions are very important. Sometimes we will say current not equal to null, sometimes we will say current dot next not equal to null. So we need to very careful whether we need to compare for the null or next dot, like next the null for the next value. So we want to compare, um, since you want the last element. So if you compare with current not equal to null, the current will go all the way to the null pointer. That's why we don't want to go to the all the way to the last address, right? Basically, you already know that the last element 1 points to null. The next pointer of the last element goes to the null. So that's why we don't want to go to that far. We want this last element, right? That's why we are comparing like this. If the current dot next not equal to null, that means there is another element is exist. That means, so we are incrementing the size. There is another element, that's why 2, and current equal to current dot next. So by the time you finish this loop, what happens is current will point to the last element, because last element dot next equal to null, correct? Last element is, let's say in the list 1, last element is 1, and that last element dot next pointer points to null. At that point, current point to last element. That's why. So we are finally, after exiting this loop, the current will point to the last element and size will be calculated properly. Okay. So now this get tile and size will give this result. So result 1 has both tile length and size, and result 2 also has the same for the linked list 2. So now what we do is step number 2. Compare tile nodes. If they are not equal, the lists are not intersecting. As I said before, we will compare the tile nodes. If the tile nodes are not equal, then we will simply say return null. There is no intersecting node because tiles are, the last elements are not equal. If they are equal, okay, now this is the step number 3. Find the longer and shorter lists. This is, of course, we can do either, we can do the difference or we can do here. So this is simple. So what we need to do is we need to figure out which one is shorter and which one is longer. So by just comparing the size, right? If the result one dot size less than result two dot size, that means list one is smaller. Did you know this simple like one line operator, what is called ternary operator or something? Basically question mark operator. I think it's in Java and C Sharp. It is available. I don't know whether this operator available in Node.js. So basically, we will
In
compare
case
this.
it is available.
Yeah, it's available, right? So basically it will compare this condition. If it is true, it will take this one. If it is false, it will take the second one. So if the size of the result 1 is smaller than result 2, then linked list is the shorter linked list. Otherwise, if the result dot size less than result 2, and this is the result 2, because longer, we, in order to find longer, we just need to reverse the values. So since the result 2 dot size is bigger than result 1 dot size, list 2 is the longer list. So by the time we reach this point, the shorter will point to the shorter list, longer will point to the longer list. We don't know which one is right. So this is interesting thing. So it doesn't matter whether you can pass the short list here or long list here. So we are having our safe here. We use the kind of safe harbor here. We will figure out based on the size which one is shorter, which one is longer. So now next one is advance the pointer in the longer list by the difference in the lengths. This is the thing we just discussed, right? So now we know longer will point to the longer list. Now we need to advance, right? We need to advance, basically advance in the sense like, okay, so if you look at here, the difference is 2. So now you're already pointing to this node, right? In the longer list, we want to go from here, we want to know the second node. Basically this is the first node and this is second node. That's what the get kth node. Basically get kth node means we are sending the longer link list, and also we are sending the difference in the size. So result 1 dot size minus result 2 dot size. So here is the math.abs. We are absolute doing this because we don't know which one is smaller, which one is bigger, right? So in order, like, no need to have another if condition, we can simply say math.abs, which will automatically returns the absolute value. So if the result 1 dot size is smaller than result 2 dot size, that means if the second one is longer, we will have minus value here, but that will automatically convert it into the plus value. So now the difference, basically difference is 2 here, right? 7 minus 5, we get 2. Ultimately we will get 2 here. And what are we doing is, longer already pointed to the first node, we want the second node from here. So get kth node. So that means we already here, and we want 2 more nodes, like we want second node from here. So first and second. Now After after completing this method, the longer will point to the exact node which we want. So let's go to that method. So here is the thing. So here is the head and here is the k, and current equal to head, and if k greater than 0, okay, so and current not equal to null. At any point of time, we need to make sure we are not reaching the end of the list, and we are simply uh, go to the next node. Current equal to current dot next. Yeah. So now current equal to current dot next, right? So now k minus minus. So what are we doing? We are simply deducting k. If you say 2, it will become 2 1 0. So once it becomes like 0, then it exit, and it will give you the current node, the exact node which will point to here. Okay, so where is that? Here is the program, right? So k starts with here, right? So k becomes since k greater than 0, it will go to the next node. Then k becomes 1, and then when this points to here, k becomes 0. That means we are currently pointed to 5. The current will point to 5. Okay. So now longer and shorter both are equal. At this point, basically both will have the same length, right, from longer. So now move both pointers until they point the same node, which is the intersecting node. Okay, so this is simple. So shorter not equal to longer. So now we need to go through the end of the list, right? Shorter not equal to longer, and shorter equal to shorter dot next, longer equal to longer dot next. So now here is the thing: return intersecting node. Simply wherever these two becomes like equal, that will be the intersecting node, right? So here we can use either the variable because both are same. Shorter equal to longer, you can return either longer or shorter. Both will point to the same node in the linker list. Okay, so we created two methods here. First one is finding the size and the last element, get tile and size, and we have a get kth node. So advancing the longer list to k elements. That is the second function. So creating these separate functions is really interesting in the important in the interviews as well. So rather than writing everything in this main method, we need to find what is the best way to separate the codes. And having this step 1 step 2 really helps. Even though you don't finish, you can simply write the steps. Here is a step 1, step 2, step 3, and here's step 5. I will do this. Like, even you cannot, like, sometimes you cannot complete the full algorithm within the given time frame, but at least if you finish, let's say, 3 steps or 4 steps, but you are on track, right? As an interviewer, I know you are on track. You can definitely finish if I give another 10-15 minutes. So that's kind of a better output rather than without having anything. So better to write the steps. Here is what I do, here is what I do, here are the 6 steps, and then start writing the code for each of the steps. Okay, any questions? Is it
No
clear?
questions. It's clear.
Yeah, it's clear.
Yeah. Now let's discuss about the complexity. So what is the time complexity and what is the space complexity? So any guess on that?
O of n is
Mm-hmm.
time complexity.
Why it is so often?
We are traversing through the list, each list once, only once.
Okay.
And space is might be O of 1.
Yeah, exactly. Because we are not simple. If we are not using any extra memory, if we are not using any extra data structures like that, class, hash tables, arrays, stacks, queues, anything, if we are not using, it's simply order of one because we are just using couple of variables, right? What are the variables here? We are using result one, result two variables, right? And we are another two more variables, shorter and longer. So just four variables. It doesn't matter how many number of, it can be million nodes, or it can be 100 nodes, or it can be 500 nodes. It doesn't matter if the length is changing, but your variables are not changing, right? Our memory requirements are same. We need just four variables. We need a memory to store four variables. That's enough. We don't need, a lot of memory. If you are increasing number of nodes, fine, we just need only four. But if you are using some data structure like stack or something in your algorithm or hash table, it may increase based on the number of nodes, because you are going to copy those nodes and put it in your data structure, right? Like a like a hash table or arrays, whatever you use. So the main purpose of using those data structures is to put the values from your inputs into those data structures. So definitely the size will increase if the input size increases, right? So but here it's constant. It's a constant number of variables. It doesn't matter whatever the size of the input. We need just four variables. Whenever there is a constant, we simply say order of one, right? So, and the other thing, so whenever there are two inputs, we better don't say order of n, because it's order of n means n is the length of the input, right? But here there are two lists. So, here, if you look at the input, right, the series, let's say there are a number of elements in the list A, and there are b number of elements in the list B. So how many
So
times we are
O
able?
of n1 plus n2,
Yeah, you
list
can
1
say n1
plus
plus n2. In this case, a plus b. A is the number of elements
oh,
in list one, and b number of elements in list two. You can say order of a plus b or n1 plus m2. So yeah, that is also perfectly fine. N1 plus n2, because we are processing, number of elements in the first list plus number of elements in the second list. So we are processing two times. Of course, these three elements will process two times, but that's not the only way. So that's why order of n1 plus n2. Cool. Are we good so far? Cicely, is it clear?
Yep, clear.
Awesome. Okay, so let's jump in. Is it okay to continue for another 15 minutes or so, or the second problem? Is it okay?
Yeah, fine with me.
How about you, Karanya? Palindrome.
yeah.
Yeah. So let's talk about the linked list palindrome. Implement a function to check if a linked list is palindrome. Okay, before going to that, I want to just run this problem, because I did not run this first one, right? So let's run without debugging. Linked list intersecting. Okay, so here is the list one. It's exact same list here: 3159721 and 46721. And these 721 and these 721 are same nodes. So that's why it is intersecting node is 7. Correct? So here in the list 2 and list 4, these 721 is different than these 721. So let me show you the test case 2. In the test case 2, I created, here is the thing. So 7 to 1 here, and again one more, another 7 to 1 here. 7 to 1. It's a different nodes. Basically all together these are different nodes than these nodes. So even though the values are same, since they are different nodes, since different addresses, so the second one is not intersecting. The lists are not intersecting. Okay. So that's the execution of this problem. Okay, let's jump into the second one. Implement function to check if the linked list is palindrome or not. So what is the palindrome? Anyone knows the palindrome?
Yes. Uh, the string or the number is same when it read from the left to right and right to left.
Yeah, A B C D. This is not a palindrome, but let's say A B B A. This is a palindrome, right? And let's say A B C B A. This is a palindrome, right? Basically, so first half equal to the second half if you reverse it, basically, right? So basically, you can think of as if you reverse the whole string. So if you reverse this one, what happens? D C B A, which is not equal to this one, right? But what about this one? This is the same string, right? If you reverse from last to the first, B A B B A, right? Even the same thing. If you reverse from the last element to the first, A B C B A, it's exact same element, same string, right? So how can you determine whether linked list is a palindrome or not? So let's say we have a linked list 1 points to 2, 2 points to 3, and 3 points to 1. Is it palindrome?
No.
No, because so if you reverse the list, it becomes 1, 3, 2, 1, which is not equal to this one. So now let's say we have something like 1, 2, and 3, and 2 points to 1. Is this palindrome?
Yes.
Yes, right? And there could be one more thing like 1, 2, 1. Is this palindrome?
Yes.
Yes. So what is the difference between this and this? It is odd number of elements. It is even number of elements. That's the only difference, right? So now how can we figure out? Any ideas? There are two approaches here. I already put it here as an input. There is a reverse and compare and iterative approaches. What are the reverse and compare? Any idea?
Yeah.
Um.
We okay.
Go
Sorry,
ahead.
you can go ahead.
Yeah, Cecilia, please.
I was just thinking that um maybe I don't know if we can. No, no, I don't think so. You
No
can go
problem. Go
ahead,
ahead.
right? Yeah.
Go ahead. Tell
Yeah.
me what are your thoughts.
We already reversed the linked list in one problem. So what I have
Mm-hmm.
done, I have reversed the given list and stored it
Mm-hmm.
in a separate linked list. So to take
Okay.
one more an extra space, reversing a
Yeah.
linked list and compare two linked lists whether they are same. If they are same, then it is a palindrome.
Yes. Exactly. That's the first approach. So basically, we will create one more linked list with the values, and we'll compare. We'll have the same pointer approach like current one, current or n1 and n2, and we will see whether they are equal or not. If any point of time they are not equal, we simply return they are not equal. So let's say we reverse this one. 1 2 3 1 becomes 1 3 2 1 two linked list, right? Now n1 points to here and 2 points to here. Once you have the two linked lists, we will compare. Is n1 and equal n1 and n1 equal to n2? Yes. Now let's go to the n2 points to second element, n2 points second element. Is n1 equal to n2? No, right? 3 not equal to 2. Simply we'll say it's
Not a
not a palindrome.
palindrome.
Yeah. So in this case, we reversed it 1 2 3 2 1. We'll compare 1 and 1, and 2 and 2, 3 and 3, 2 and 2, and 1 and 1. So finally, we'll able to complete everything, the entire n1 and n2 equal all the time. So it's a palindrome. Same thing for this, right? So 1 2 2 1, and we'll compare. So the main uh, so this algorithm works, but what is the main drawback or the downside of this algorithm?
Extra
Extra
space.
space.
Exactly. So if you have 5,000, you are taking another 5,000 elements and compare. So how can we do this in an efficient way?
I have a quick question before
Yeah.
proceeding.
Yeah.
Um, so if we're using extra space, uh,
Yeah.
how are we storing it? Are we reversing it and then storing it in the and the
We
linked
are
list? Or
storing that's a good question. We are creating entirely new linked list. Basically, we are not touching anything here. We are not touching any of the nodes because we want to compare. We want to maintain the given linked list as it is, right? So what we are essentially doing is we are creating another new node which have valued the value of the last element, and then we will create another new node with the value of this element, and that
okay,
kind of thing. So we will basically create a new linked list which will point from the last element all the way to the first element.
okay.
Yeah, so it's completely new set of elements and without touching any of the initial linked list. So that's why if you say order of n, like there are n elements, we need another order of n space because we are storing n more elements in the memory, right?
Okay.
Yeah. So and what about this is space complexity? We need n space, order of n space, and time complexity. What is the time complexity here? So basically, how many times we are iterating?
Is it order of n?
Yeah, order of n, and of course we can say two times, right? But still, it's order of two n is n because order of n means first we are creating the second linked list by navigating all the um, elements, and then we are comparing, right?
Mm,
So it's order of 2n. Order of 2n is basically order of n. 2 is just a constant value. So yeah, it's order of n space and order of n time complexity. So is there any way to reduce both? Actually, there is a way to reduce both the space complexity and also time complexity.
Can you use two
Any idea?
pointers?
Two pointers for what? Without even creating, because we are using two pointers after creating a linked list here n1 and n2, right? So you want
Okay,
to use
okay.
two pointers without creating second linked list. Yeah, yeah, it might be a good idea. Tell me how to do that. So if
Um,
you use two pointers, okay, go ahead.
I was thinking to put like a pointer in the head and another pointer in the tail and then traversing.
That is the main drawback of linked list, right? You
Yeah.
cannot, you don't know the last element. I know if you traverse all the way you can figure out the last element, but you cannot navigate back, right? You can compare these two. So how can we navigate to this element in order to compare with this element, right? I totally
Mm-hmm.
agree with what you're saying. Basically, if this is array, right? If it is a simple array, we can have two pointers, one from the beginning, one from the end, and we'll compare each element until they collide or until they meet at the middle, right?
Mm-hmm.
Yeah, but that's not possible in this case, right? Because of the because of the way the linked list works. You cannot navigate. If it is double linked list, that's a good idea. It's very easy. You can have pointer at the beginning, pointer at the beginning, and the pointer at the end, and you can compare and you can navigate to the middle. Okay, Karunya, any ideas, or should I go ahead and tell you the solution?
No, I don't have any idea.
Okay, so here what we can do is it's almost the same solution like the comparison of the half and half. So, but we will use extra memory. So, let's say I will give one more clue. If you use any extra storage or extra data structure, what data structure would you use?
Back.
That's right. You got it. Stack is the answer. So what is the advantage of stack here is, so if you, let's look at this element here, let's look at this first linked list 1 2 3 1. So what we need to do is basically 1 2 3 1 is not palindrome, because we are simply looking at this half and this half. We are comparing these two, we are comparing these two. These two are equal, but these two are not equal. So what it meant by that is basically you will, if you have these elements in stack, let's say these elements in stack, then while you going to these elements, you can compare with the top of the stack. So what I'm saying is, so what we do is we will put the half of the elements of the linked list in the stack. What is the half? We will put 1 here, and then we will put 2 on the top, and then we will stop there. Now while navigating second half, we are comparing each element with the top of the linked list. So we already put half of the elements, 1 and 2 is here. Now while navigating 3, is 3 equal to 2? No, right? Then simply say this is not a palindrome. Let's look at the second example. So second example, we'll put 1 here, 2 here, and now uh, we know it. We should not put 3, because what we do is, if this is the odd number of elements, if there are odd number of elements, we will just put the first half of the elements into the stack. We don't need to put the 3 there, because there is no another 3. We can just ignore 3, right? We simply compare these two and this two, and this one and this one, right? So now what we do is, we'll ignore 3 and we will compare with this one. 2 equal to 2, yes. And then what is the next value? 1 equal to 1, yes. And finally, by finishing this whole navigation, like and the stack will be empty, and both are palindrome. The second one is palindrome. So we are not creating any separate reverse linked list. We are simply putting half of the elements in the stack. Okay, let's compare this value. Let's look at this one. 1 2 4 5 1. Okay, now what we do is, we'll put the stack here. 1 will be in the stack and 2 will be in the stack, and as I said, we'll ignore 4. Now while you going to the next element 5, we'll compare, is 5 equal to 2? No, simply we'll say not palindrome. Or let's say we have let's take one more input. 1 2, okay, 4 2 6. So what happens here? 1 2 will be in the stack, and 4 we will ignore 4. Is 2 and 2 are equal? Yes, 2 and 2 are equal. Now let's go to the next element. We'll remove 2 from the stack, and 6 and 1. Is 6 and 1 are equal? No. So it's not a palindrome. Did you get the solution?
Yes.
Yes.
So basically we are just storing half of the elements. So the space complexity is reduced by n by 2, correct? At most, half of the elements. If you take these 5 elements, 5 by 2 is like 2, because don't take the point value. So 2 elements. So we are reduced n by 2, and also we are navigating only once. See, we are navigating 1 and 2 and put it there, and 4 we will ignore, and 5 we compare with the top of the stack, and 1, the last one, will compare with the next one. So basically we are navigating order of n times. So navigating is also only one time. In case of reversing the list, we are doing order of 2n, right? We are navigating all the elements and creating a reverse linked list, and then we are navigating again to compare the elements. So both the time complexity and space complexity is also reduced. But the problem here is how to figure out how many elements we need to put in the stack. As I said, we will put only first half. How do you know what is the first half? We are, as we are going through the linked list, we need to stop at this 2, right? As you are going to this, we need to stop here. We don't want to put 4. We just need to put until the first half. So how can we figure out that part here? That is the only catch here. If we have 9, like if we have 100 elements, we need to stop exactly at 50 elements. If you
What
have
if we have
101,
odd number of elements? Separation.
yeah, here is the thing, odd number of elements, right? Here, what is the number of elements? How many number of elements in this list? 1, 2, 3, 2, 1, right? So 1, 2, 3, 2, 1, which is 5. 5 by 2 equal to 2. We will just take these many elements. So in order to reduce, like basically one thing what we can do is we can simply go to the navigate the entire list and find out the length, and then do the divided by 2, and we'll get this number, and then navigate again and put those numbers in the stack. But there is a simple way to do that. You don't need to calculate the length, and you don't need to do this division. You don't need to do this. These are all can be possible with a technique called two-pointer technique, which is already Cecilia told before. Two pointers, by taking 2 pointers. So we already discussed, I think last time, right? What is that? The kth node from last, those kind of things. Two-pointer technique, right? So fast pointer and slow pointer. Even we when we discussed about the loop, finding a loop, right? So what I'm saying is, by having 2 pointers, so one is like slow and second one is fast pointer. By like slow pointer will only go to the one element, but fast pointer will jump to the 2 elements at the same time. So the catch here is, by the time fast pointer reaches at the end of the list, slow pointer exactly at the middle, right? So basically you have 100 elements, and slow will go to the 1, 2, 3, 4, 5, something like that, and fast pointer will go to the 1, 3, 5, 7, 9. It just jumps 2 point, like 2 numbers at a time. So by the time f reaches 100, slow, the slow pointer s will be at the 50th location, correct? Because it's divided by 2, right? It's the slow pointer will move only half of the mouse, but fast pointer will move double the mouse, and it will reach the end of the linked list. So correct? Any questions there?
No.
Yeah. So that's the main catch here. By using slow pointer and fast pointer, we can exactly figure out the um, mid of the linked list. That means we will simply put the elements of the slow pointer into the stack, because slow pointer will navigate to each and every element, right, until the middle. But fast pointer will ignore, because fast pointer, by the time it reaches the last element, we will stop adding elements to the stack. And then what we will do is, we start popping the elements and comparing with the rest of the elements on the stack, on the linked list. Okay, so I can show the problem, and we can let me know if you have any questions afterwards. Here is the 2 methods, as I said. So here is the given linked list. Test case 1, 1, 2, 3. Simple 1, 2, 3. Is it palindrome? No, right? Second one is 1, 2, 3, 2, 1. This is palindrome, right? So this is test case 1, test case 2, and test case 3 is 1, 2, 2, 1. So basically this is odd number of elements. This test case 2 is odd number of elements here. 3 is in the middle, 1, 2, 3, 2, 1. And here is the even number of elements, 1, 2, 2, 1. Right? This is the even number of elements. So now print list, which is printing the list. And here is the reverse and compare method, which we just discussed. So here is the thing, is palindrome is the main method. So head, we are simply pointing the head, and bool, is it true or false? So now As I said, reverse and clone. Basically, we are cloning the linked list. We are sending a head here, and we are asking this method to reverse the whole linked list and clone it. Cloning in the sense we are not modifying anything on the given linked list. We are simply creating a separate linked list, and that is the reversed list head. That is the pointer which points to the reversed list, head of the reversed list. Now we are calling is equal, is both are equal, right? So let's look at those methods. First one is reverse and clone. So this is also, this particular method itself is another interview question. Write an algorithm to clone a node or clone a linked list. Cloning a linked list is one thing, and reversing and cloning is another thing. So here is the algorithm to do that. So it takes little while to understand. So basically what are we doing is we are creating head equal to null, and node is the node, and we are creating new node. And what are we doing here is we are creating new node with the value of the data, with the value of the node, and node dot next equal to head. So this is very typical trick, little bit tough to understand. So how to reversing is, let's say 1. So new node nn, let's say nn equal to 1, and nn dot next equal to head. That means head is pointed to null right now. So this pointed to null, right? And now head equal to new node. So now we are saying head equal to null. Now head equal to new node. This is head, new head. Now node equal to node dot next. So node dot next is 2, right? So now what happens is we are creating new node with data. So we are creating another node with data 2. Now node dot next equal to head. That means 2 dot next equal to 1, and head change it to 2. Head equal to new node. Whatever the new node you are creating, that you are calling head. So it's creating a node, creating a new node, and pointing that node to the existing head and changing the head afterwards. So this way, by the time you create 2 and you create 3, 3 points to 2, and head becomes 3, and you create one more item 1. You create 1, 1 points to 3, and head points to 1. So that's how we are reversing the whole list. We are recreating 1, 3, 1, 2, 3, 1. So now, finally, by the end of this method, head points to 1, and from 1 you can, if you say what is the next value, 1, 3, 2, 1. Basically, you got the reverse of this whole linked list, 1, 3, 2, 1. Got it? So that's the whole reverse and clone method. We are keep changing the head until you find last node, and then we are returning that head. So that is the main logic here. And once you have the reversed head here, we are comparing. This comparison is simple, I guess, because head not equal to null and head 1 not equal to null, head 2 not equal to null. At any point of time, both are not, the data is not same, simply return false. Otherwise, head equal to head dot next, head 1 equal to head 1 dot next, head 2 equal to head 2 dot next. Simply we are navigating, both the nodes. So if you look at here, right? So in this situation, we will get 1, 3, 2, 1. So 1 equal to 1, but 3 not equal to 3 equal to 2. No. So simply it says 1, 2, 3, 1 is not a palindrome. Okay. So now the next one here is the last node. Like what happens here is if both are null, and then we simply both are null means we successfully navigated both the linked lists until they reach endpoint, and both the values are same. At any point of time, the value in the head 1 is equal to value in the head 2. That's why we simply call it's a true. Okay. So that is the algorithm for reverse and clone, and basically the reverse and compare method. So I can run the code and show. Any questions so far?
No.
Is it clear?
Yeah.
Yeah. It requires a lot of practice. Basically, the first one is understanding the problem. Second one is coming up with an algorithm. Hey, what is the approach and what are the complexities, time complexity, space complexity. And third one is the practice, like how to write these algorithms. So even though you have an idea, but while writing itself, it takes time, right? So here is initial list. 1, 2, 3. Is it palindrome? 1, 2, 3 is not a palindrome because 3, 2, 1, right? And the next one, 1, 2, 3, 2, 1. It's a palindrome. And here is the even number of list. 1, 2, 2, 1 is a palindrome too. So now if you want to look at the iterative approach, as I said, we need stack. And we also need 2 pointers, right? Fast and slow. Okay. So we took a stack of integers because stack, we just need to store the values. We don't need the full nodes, right? We are not recreating the list. We simply store the values and we'll compare. That's why I took the integer stack here. So now step 1, push half of the elements into the stack. So how can we push half of the elements? By using fast and slow pointers. So fast not equal to null and fast dot next also not equal to null. That means push stack dot push slow dot data. So slow is the slow pointer to the first element, and slow simply say slow equal to slow dot next. But fast equal to fast dot next. So it will jump. It will jump 2 items at a single step. So by the time fast reaches end of the list, we pushed already. We pushed half of the elements into the stack. So here is the important step here. If fast becomes null, it means there are odd number of elements in the list. So skip the middle element. So how to skip the middle element? Basically, we simply navigate slow one more time. So let me give an example. So let's say we have these elements like this: 1, 2, 3, 2, 1, right? So fast will be here, slow will be here. So both at the same time. Now fast will jump to this element and slow will jump to this element. Fast will jump to this element and slow will jump to um, this element. Okay. Now fast will become null. Wait, is it become null or not equal to null? Not equal to null. See that? Fast not equal to null. Yes, because by the time you exit the loop, right? This loop will be exited because fast dot next is null. Fast dot next is null. We are exiting the loop here. Now fast becomes, if the fast becomes not equal to null, not equal. I think I put a wrong word here. So if the fast not equal to null, which is right at this point, that means we have odd number of elements. When you have odd number of elements, you simply move the slow pointer to the next element. We are ignoring, basically we don't put this one into the stack. We will put only 1 and 2 into the stack. We don't put this one into the stack. We simply move slow pointer to the next element. Let's compare with the even number of elements: 1, 2, 2, 1. Okay, fast will be here, slow will be here. Now fast will jump to this element, slow will jump to this element, and fast will jump to the null here, right? Now at that point, right, we simply exit the loop, and we already put, no, slow already here, sorry. Fast will jump to the null element, and slow jump to this element. Now fast equal to null. Whenever the fast equal to null, we no need to do anything. We no need to, slow is at the right position, which is something we can compare with the top of the stack. So that's why we don't advance slow in that situation. So is it clear why we have this situation? This is basically ignoring the middle element, uh, for comparison. I hope it is clear. So now let's look at the while loop. This is simple. As I said, now proceed with elements in the list and compare them with elements in the stack. Since slow at the right position, if slow not equal to null, until slow not equal to null, top, what is the top element? Let's open the top element or pop stack dot pop. That will give you the top element. and we'll compare top not equal to slow dot data. If at any point of time, if the values did not match, we simply say not palindrome. If they are matching, we simply proceed to the next element. Slow equal to slow dot next, and then again pop, compare, slow equal to slow dot next, again pop and compare, and finally, if the slow equal to null, that means you completely process the rest of the elements and it matched all the elements from the stack, and finally you return true because that is a palindrome. Okay, is it clear? This is step 2, and here is step 3. It is tricky, but um, while understanding, like while how, by looking at how the stack works, right? Stack will give you this in a reverse order, and that's what we want, right? We want to, while you're going to the half of the second half of the linked list, we just need the reverse order of the elements. That's why queue doesn't work here. Only stack is the correct data structure, which will give you the ability to compare, in a reverse order. Okay, any questions?
No, but Suresh, could you please share this solution right after the session? Because
Yeah,
I,
yeah, sure. I will share it. So, is it something you're practicing tonight itself?
yeah,
I will. You want me to share immediately?
yeah,
Yeah, sure, sure. I can do that. Yeah, but do you like the solution? Is it clear?
yeah, it's clear. Yeah, it's
Yeah.
clear. Good.
Go through, go through the solution again and to see how it works. Yeah, it definitely helps to, practice and understand each and every step. I tried my best to explain, but again, I know it is like first time looking is always confusing, right? Yeah. So in order to run the second solution, what we need to do is we can just comment this first approach and open this one, is palindrome iterative. Okay. And the same thing for the second one, is palindrome iterative. So it's exact same answer, but so it's a two different approaches, right? So we can run it. It's the same answer. Cool. I think it is helpful. How about this, Cecilia? Is it helpful, or
Yeah, really helpful. Thank you.
is it complex, or how? Yeah, I don't know. Give me some feedback whether is my
Um,
explanation is okay or any changes required. Am I going fast?
no, no, explanation is very good. I just need to practice. Yeah.
Yeah, that's right. Okay, here is initially same thing. Palindrome false, is true and true. It's exact same output, but the complexity is different. Yeah, cool. If you don't have any other questions, we can wind off and we can meet again next week. And if I get the recording, I will share the recording.
Yeah, thank you,
Yeah,
Suresh.
Soumya messaged me too. She want the recording, it seems.
Yeah, yeah, sure. I will try to put it in the couple of hours. I will put it in the channel. I will save somewhere and we'll see. Great.
Okay, thank you,
Okay,
Suresh.
let me
Thank you,
stop
bye.
recording.